I didn't make an announcement about this, but maybe I should have. I posted the test with all the answers in it, so you can look it over if you want. So if you go to web courses and you go to the files tab, web courses, files tab. Oh, look, you get to see here's my password, it's a bunch of dots. Here's my pin, it's a bunch of dots. So yeah, it's in the same place I always put stuff. It's in the files tab. I'm just showing it so if anyone has any questions, they're hopefully answered. Files tab, test 2, and ta-da! 2053, test 2, student version, answers, and it's student version A. All right, there's 2 questions that the vast majority of people missed. I'm going to talk about both of those. I'm going to give the joke of the day first because otherwise I'm going to forget. All right, this one's going to be wordy. What's the difference between a dapper man on a bike and a poorly dressed man on a unicycle? Attire. Because attire, like they're dressed. They're so again, found all the good jokes online. Anyway, I like them. All right, so test this here. I'm just going to point out the questions that the vast majority of people missed. So number 5 was the one that, honestly, it's not. It would have been better. My goal with this question was I wanted to specify the log. This one I was specifically talking about the log, not the ax and the log together. I didn't clarify that, which is why I gave some points for B or C after reading it through. If you answered C, I actually did give you points for it instead of the curve points, so you got like maybe 1% extra kind of thing. Whatever. The goal is the log, and momentum is always basically conserved as long as there's no some extra things going on. So momentum is conserved because you start with something together and it splits, and momentum is conserved. Great. Energy is not conserved in the log, and this is really easy to prove if you just think about numbers. The log starts at rest. What's its energy? 0. It's not moving. It's got no energy. Then the log splits. They both have some energy. Something doesn't equal nothing. So it's really easy to prove that if you just make up numbers. It would have been better, as weird as this sounds, if I had said a log's sitting somewhere, it then explodes into 2 pieces. And the same would be true. Energy wouldn't be conserved because you start with no kinetic energy and you end up with lots of kinetic energy. But momentum is conserved. So basically I just wanted this question, the purpose of it, elastic collisions, when things bounce off each other, energy and momentum is conserved. When they bounce off each other. When 2 things stick together or split apart, energy is not conserved. Literally, if 2 cars hit each other and get stuck together, energy is not conserved because some of the energy went into the deformation of the material, literally getting squished. Deformation is a fancy way of saying it got squished. All right, the other question that got missed was this one, and this is one I tried to emphasize in the review beforehand. So we'll talk about this one, and it'll be hopefully an aha moment for if you missed it. I pull a 10 kilogram box with a force of 50 newtons up a slope of 30 degrees. If my force is parallel to the surface, and the box travels 3 meters along the ramp, how much work did I do? So this is the Fx cosine theta. F is up the ramp. Delta x is up the ramp. The angle is the angle between F and the direction you're going. The angle between F and the direction you're going in this is 0. If you just chuck the 30 in there, you get the wrong answer. So the math here was actually super easy. It was 50 times 3 times cosine of 0, which is 1, so it's 50 times 3. This question was checking, do you know what that angle represents in the formula? Do you know what that cosine theta, that it's the angle between F and the direction of motion? Or are you just kind of putting any angle in there? And then the rest of it, pretty much every problem, at least 40% or more, 40, 50%, at least 45% of people got every other question right. So that's kind of a good sign to me. As weird as that sounds, if around half the people are getting the question right, that means I played some role in that. The 2 questions I mentioned were about 30%, which is getting to like random chance, which means I didn't play a role in anything, which is why I give some points back. That's kind of how I determine that. I am the common denominator. If the amount of people getting it right is basically equivalent to random chance, then I did not do anything, which is not a good sign, since I'm the common denominator. All right, great. So there's that, the things there. Oh, a really common question I've been getting is the new content. How much of the test is going to be new content? My answer to you, actually, I'm going to go back to the Files tab. We have about roughly 12 weeks worth of content. These last 2 weeks are technically 3 weeks, so these should technically be like 3 weeks. You can basically think of each week as being an equivalent amount on the test. So there's basically been 12 weeks total. So our first test is weeks 1 through 5, so maybe about 5/12 of the test is test 1, about 4/12 is about test 2, give or take a few questions. And then the last 3 weeks, I know it says only 2 weeks here, but we're doing it over 3 weeks. The last 3 weeks is the stuff we're covering now. So about each week of class counts for whatever we covered that week. That's how representative it is. We've had 12 weeks of content. So each week is going to be 1/12 what's on the test. So about 2/12 of the test will be forces, 2/12 will be kinematics, because there's 2 weeks for each. Does that make sense? 12 weeks, each week is represented equally. All right. Long story short, if this is just the easiest way, the stuff we're covering will make up about 25% of the test. Rotational motion will be about 25% of the test. That's probably the bigger answer that people want. The rest of the test will be roughly split up between test 1 and test 2. Yay. Okay, so any questions about the final will be in this room at the time I put on the syllabus, which I don't remember. I think it's like 1 to 350 or something. I don't know. It's on the syllabus. I'll have to double check. Any questions, comments, concerns? All right. Rotational motion. Let's see. Where did we finish off last time? Awesome. We finished off right where I wanted to. Okay. So I taught you all centripetal force. So last class we talked about centripetal force, which is a little math trick that lets you find, if you have a circle, and you got something going in a circle, and there's forces. Remember, F net equals MA? MA equals sum of all the forces. If you're going in a circle, it turns out that A equals V squared over R. And so MV squared over R equals sum of all the forces pointed inwards or outwards. If it's pointed inwards, it's positive. If it's outwards, it's negative. And we did some practice problems on this. You had the roller coaster at the top. Normal force and gravity were both inwards, so mv squared over r equaled Fn plus Fg. On the bottom, Fn's up, inwards, Fg is downwards, so it's Fn minus Fg. On the side, normal force was the only force pointed inwards, so mv squared over r equals Fn. Sum of forces, inwards and outwards, equals mv squared over r. And then we did a problem, and I mentioned the car. If you're looking at a car going from above, the only force pointed inwards is friction. That's the only reason you can turn. The only reason your car can turn is if there's friction. No friction, you can't turn. If you're going over ice and your car can't get traction, you're not going to be able to turn. You will just slide. That's why ice is so dangerous. You can't change direction. You're about to hit something, great, turn the wheel and nothing's going to happen. Your tires only turn because of friction. If you don't have friction, you can't turn. We are blessed in Florida to not... You do experience this if you hydroplane. Hydroplanes, when you go over water, you don't get friction anymore. You can't turn. It's kind of scary. When you hydroplane, your wheels literally are skimming across the water, i.e. they're not touching the ground really anymore, which means you don't get friction, which means you can't turn. So be careful on wet roads. And also, fun fact, the treads in your tire aren't actually for better, like a little bit better friction. The main reason you'll have treads is to make the water have ways to disperse. If you had a flat tire, the water would not spread out. Literally, the reasons for the treads is they're channels to like make the water go away. If your tire was completely flat, the water is going to get trapped. And if the water gets trapped, it's really slippery and you lose traction. So yeah, make sure your treads are good on your tires. No treads, bad traction. It's going to start raining hopefully in a month or so. It's really, dangerous. Anyway, we then practice direction stuff. So we did this right-hand rule. If you want to figure out the direction of angular velocity, you make your hand spin in the direction you're going, and your thumb points in the direction of angular velocity. If you want the direction of angular acceleration, you need to decide whether you're spinning faster or spinning slower. Acceleration points in the same direction of velocity if you're spinning faster. Acceleration points in the opposite direction if you're slowing down. So you got to figure out which way you're spinning and then decide whether acceleration is the same or opposite. And we practice that. Yay, so much fun. All right, and then this was the thing I need to, these are some new things. Remember that angle, theta, is measured in radians. Do not do these problems in degrees. It will not work. Remember, 360 degrees is made up. Why is it 360? Because some human at some point decided. 2 pi is not made up. 2 pi is based on the way the universe works. 2 pi is the ratio of the circumference of a circle to the radius of the circle. It's set. No one at any point decided for 2 pi to be one full circle. It's based on just the definition of a circle. So 2 pi is like the real angle. 360 is made up. Whatever. There's 2 pi radians in 1 revolution. And then I showed you all this slide, and I'm going to kind of put all the things here. So rotational kinematics is the same as linear kinematics. You just swap the variables. Instead of x, theta. Instead of v, w. Instead of a, alpha. All the same things. And then if I want to go from angle to x, what do? Times it by r. Great. If you want to go from angular velocity to velocity, what do? Multiply by r. And yeah, you got the idea at this point. You want to go from angular acceleration to acceleration, you multiply by r. This is only true for these 3 angular variables. All the future ones I'm going to teach you, it doesn't necessarily follow, but these ones it works great. And then, remember that there's 2 pi radians in 1 revolution. That was in the last slide, but this is basically all you need to solve most of the problems. So, we're going to do a couple more steps. I started a problem with you all. Before we get to that problem, I want to check if you all understand the difference between angular velocity and regular velocity. So, I have a much prettier problem than my usual problems because someone else made it. The other person was Dr. Doty. She has rabbits, hence the rabbits. Anywho, she makes much more aesthetically pleasing slides than me. So I got 2 bunnies. You can't read it, but 2 bunnies sitting on a merry-go-round. Bonnie here is on the edge. Clyde is somewhere in between that and the middle. Doesn't matter where, just somewhere in between. The merry-go-round makes 1 complete revolution every 2 seconds. Is Clyde's angular velocity the same as Bonnie's, twice as large as Bonnie's, half of Bonnie's, or 4 times Bonnie's? How does the angular velocity of Clyde compare to Bonnie? And this is checking, does angular velocity make sense to you? And you could do this mathematically if you want. I actually gave you numbers. So if you want to double check, calculate the angular velocity of Clyde. Calculate the angular velocity of Bonnie. The math should always match the logic. The idea. And check with your neighbor, check with your friend, make a new friend, all those things. All right, we'll go like 10 more seconds. All right, we'll close this out in 5, 4, 3, 2, 1. Oh, I wish I had a meter stick in here. All right. So, angular velocity. What is angular velocity? So, what are the units for angular velocity? That's going to help us if you all remember that. Regular velocity is in meters per second. What's angular velocity in? Radians per second. If we know the units, it helps us remember how to what the heck it is. The units tell you what's going on. Angular velocity is how many radians are every second. Now, radians is not something you're probably familiar, maybe not super comfortable with. Radians is just angle. Remember, radians is just a measure of angle. Pretend like it said degrees per second instead. It's the same idea. How much does my angle change every second is what this says. We just happen to measure angle in radians. But pretend like it says degrees per second if that makes you more comfortable. Okay, so let's take the extreme. And I even gave the numbers for this. So the equation for it is literally the change in angle over change in time. Let's do the numbers I gave you. I gave you 2 seconds. How much is my angle change? What's the radians? I'll rephrase it. I make 1 complete revolution. What's that angle? 2 pi. Did we pick a bunny to solve this? No. The answer is the same for both. Angular velocity is how much angle changes per second. These both make an entire circle in the same amount of time. So anything that's on a disk has the same angular velocity. Notice I didn't care where Clyde was. The angular velocity doesn't depend where you are on the disk. It's how many times does that thing spin per second? Doesn't matter where you are, you're still going to spin the same rate. So that's something that's kind of different. Angular velocity is the rate of spin. How fast am I spinning? Doesn't matter where you are on this, you're spinning the same rate. So let's see how that landed. Yeah, it's a little bit of a tricky thing. The angular velocity is the exact same because they both make 1 full circle in the same amount of time. All right, what about tangential velocity? Tangential velocity, we just put the word tangential in front of it. It's the same as regular velocity, the stuff you're familiar with. Just now we have an angular velocity, so we're going to put the adjective tangential in front of this one. It's just v. How do their velocities compare? Last one was angular velocity. This one's regular velocity. Tangential velocity. Which one has the bigger tangential velocity? Which one has the higher velocity? Does Clyde have a higher velocity or Bonnie? Bonnie's on the outside, Clyde's on the inside. Which one has a higher velocity, or is it the same? All right, we'll go 10 more seconds. All right, we'll close it out in 5, 4, 3, 2, 1. All right, so I'm going to explain it. I'm going to connect it to reality first, and then we'll do the equation to get the answer. You can't see this online, but I'm holding a ruler. If I swing this ruler, what part's going to hurt the most to get hit by? The part that's farthest from my hand. Why? Why does the outside hurt more? It's because it's traveling faster. Why is it traveling faster? All of this, when I swing a stick, all of it's rotating at the same rate. The change in angle is the same. But this one has to travel a farther distance. The end has to travel a farther distance. And it's really easy to prove that if I just hit this on a desk and it got louder because it's literally traveling faster. So again, this is stuff that you're familiar with. Getting hit with a long stick hurts. Why? Mathematically, remember, if you want to go from angular to regular, multiply by r. Bigger the r, bigger the v. Everything on the circle has the same w. Angular velocity is the same everywhere. But if r is bigger, so if I draw r here, that's r for Bonnie. This is r for Clyde. And Bonnie literally has to travel a bigger distance to make it around the whole circle. It has to go faster to do that. They're both traveling a circle. Bonnie's got to travel faster to make that circle in the same amount of time. So there's many ways to kind of think about this. If you've ever ridden one of those rides, if you've ever ridden any of those children rides that spin in a circle, if you're on the outside of that circle, you feel like you're going to fly off because you're literally traveling faster. And therefore your centripetal acceleration is larger, mv squared over r, and all that good stuff. Okay, I didn't do this problem, but I'm going to continue on with this one. So this is the one we started last class, and it's like, oh my gosh, so many words. It's just a kinematic, it's not as bad as it looks. So we started with step A. So we had a car that's stopping, it decelerates at 7 meters per second squared. And I said, what's the angular acceleration? That was the first step. Just what's the angular acceleration? It was so easy. If you just remember that to go from angular to linear, you multiply by r. If we have the regular acceleration, and I want to go to angular acceleration, I just divide by r. Do you want to go from angular to linear? Multiply by r. Do you want to go from linear to angular? Divide by r. And so we did that. And we took the negative sign because we're going to say the car goes to the right. So therefore the acceleration is to the left, so it's negative and yay. Great. Part B, how many revolutions do the tires need to make? So this one, we had to use a new skill. This was a new skill in part A. But in part B, we had to realize that there's 2 pi radians in 1 revolution. That was the thing we had to do. So if we can figure out the angle, if we can find the total angle that it changes, divide it by 2 pi, and that's how many revolutions. And I gave you all the example. If the change in angle is 8 pi, how many revolutions is that? If my angle is 8 pi, it's 4 revolutions because it did 2 pi, then 2 pi again, then 2 pi again, then 2 pi again. So 180.5 radians might not sound as nice as 8 pi, but it's the same logic. Just divide it by 2 pi and boom, we have the revolutions. So we did that last time. All right, now we're going to do the rest of the problem. We'll do the rest of the problem. Why not? So I got my big old list of givens here. I'm going to make a new list of givens on a new slide just to organize everything because we've done a bunch of stuff at this point. So our new list of givens, just to kind of write it all out, we have our acceleration was -7. I'm pulling this from the problem, not pulling it out of thin air. We found the angular acceleration in part A. The car did it start at rest or end at rest? It ended at rest. So its final angular velocity is 0. Its final velocity is 0. It's not moving. The tires aren't spinning. They're both equal to 0. Our initial angular velocity was 95. That was given. I didn't pull that out of thin air. It's given in part B. Its initial angular velocity is 95. All right, I'm just going to keep jotting down things. We just found that the change in angle was 180.5 radians. We found that by doing angular kinematics, just regular kinematics with angle stuff. And sure, if you really want, the number of revolutions was 28.73. We're not really going to use this. You could if you wanted to, I suppose. Awesome. Big old list of givens. You got linear variables and you got angular variables. Just for funsies, we haven't done it yet. I have initial angular velocity. What if I wanted to find, just so we have both versions, we have acceleration, angular acceleration. We have final velocity and angular velocity. We have initial angular velocity, just for funsies. See if y'all can find initial velocity. See if you can figure out how would I do that? I have the angular version. That's my hint to you. How do I go from the angular version to the linear version? We're going to multiply it by r, which I will chuck down here. If you all want to go from angular to linear, multiply by r. So 0.28 times 95 equals something. And that's how fast our car is moving. Yay. Fun fact, this was actually question D. Nope. We solved part E. Yay. Part E was what's the car's initial velocity. But it's that easy. 26.6, which is roughly 60 miles per hour. Remember, 27 meters per second is 60 miles per hour. All right, great. We did part D. So we'll just chuck that down here. V naught equals question mark. Oh, there it is. Done. All right. Didn't even realize it was a question. Well, I knew it was a question, but. All right, part C. Part C says how long does it take... Oh, sorry, we saw part E. My bad. Part C says how long does it take the car to stop completely? How long does it take? What are we solving for? Time. Great. All right, y'all got a bunch of givens. You need to make the decision. Do I want to solve for time with my linear variables? Or do I want to solve for the time with my angular variables? It doesn't matter. Just pick one of them. We have the angular and linear version of all of them. We haven't found distance yet, but if you wanted to, you could solve for distance. In fact, part D is find the distance. So, try it out. Pick your poison. Look through your formulas, given our givens. What equation will let me solve for time? Use either the angular or the linear one. Both work. You get the same result. All right, so we have acceleration, both types. We have velocity final, both types. We have initial velocity, both types. We also have the change in angle. So here's my big old list of equations. Given what we have, what lets us find time? Which one do y'all want to use? There's many options. Let's just go through the list. Does the first one work? Yeah, do we? All right, great, there's time. That's important. Do we have final angular velocity? Yep. Do we have initial angular velocity? Yep. Do we have angular acceleration? Yep. But if you're like, man, I prefer linear, great, you could do it. It works the same. So this is really a preference thing. If you really want to work in linear, just take your angular variables and divide by r. Or sorry, multiply by r. And then you can work all in linear if you so desire. And then go back when you want to. It all works out. So, if you want to find time, you can either do VF equals V naught plus AT, or you can do omega final equals omega initial plus alpha T. Both ways will get you there. I'll use the new one just for funsies. So I'll use this one. They both work. 0 equals 95 plus negative 25 times t. If you solve for t, it's just going to be 95 divided by 25. You get 3.8 seconds. Yay. Answer done. If you really want, you could instead have done 0 equals 26.6. You could have done this other one. Like I'll put it here because it doesn't take that much time. 0 equals 26.6 plus negative 7 times t. And you get the exact same answer. Maybe with some rounding. Cool. All right. Part D. Just to get us kickstart on that. What distance does a car travel? What am I solving for? Distance. What's our variable for distance? It's going to be x, and we'll do delta x. If you want, you can make it x final and just make x initial 0. That's fine. But delta x is a little bit more all-encompassing. All right. Figure out how you all want to solve for delta x. There's so many options. We have literally solved for every single other variable in this problem. So you have like all the options at this point. Just like when you all did kinematics, the more puzzle pieces you get, the easier it is to solve. There is one really easy way though. And there's ways that are fine, but take a little longer. All right, you have so many options here. I'm going to list the ones that take longer, and then I'll do the easy one last, and that's the one actually I'm going to do. Delta x equals v naught t plus 1/2 at squared. Totally works. You got everything. You could chuck that in there. You could do vf squared equals v naught squared plus 2a delta x. Totally works. You got vf, you got v naught, you got a. Chuck them in there. Great. All of these are more work than you need to spin, though. Do we have the angle? What's the rotational analog for delta x? So delta x, remember, if you want to go from the rotational version to the linear version, you just multiply by r. What's the rotation version of delta x? It's theta. And if you're ever unsure on this, literally just look at the equations. And everywhere there's an x, there's a theta. If you're like, I don't remember which one goes with which. Everywhere there's a v, there's a w. Everywhere there's an alpha, there's an a. There's also literally these equations at the top. Those are on your formula sheet. So the really easy way to solve this, we have the change in angle. We found it in a previous problem. Just multiply it by r and you're done. That'll tell you how far you traveled. It's that easy. If you really want, you could go through all the kinematics. Totally works. Nothing wrong with that. But this is if you have the rotational version, just multiply it by r. And you're done. So that's like our new thing we learned in this whole thing is that we have these rotational variables and you can go from linear to rotational. You can go from rotational linear by multiplying by r. You can go from linear to rotational by dividing by r. Opposite of multiplication. And that's the whole problem. The last one is this reasonable? And the answer is yes. There's a reason speed limits exist. Regardless of how good of a driver you are, your brakes only slow you down so fast. And it is very dangerous to go 60 miles per hour where there's kids at play because if a kid runs in front of you, you're not going to have 50 meters to stop. So, Anyway, that's why people get really, really frustrated with people driving fast in residential neighborhoods, because the laws of physics, your brakes only work so well. They don't make you stop instantly. It takes quite a lot, way more of a distance than you expect to stop. This is also why you shouldn't tailgate people, because if they slam on the brakes, you don't have that much room. Yeah, that was actually first car accident was 2 weeks after I got my license. It wasn't my fault. It's always important to say, right? Yeah. Well, this one I didn't hit. Well, okay. So the car in front of me stopped. I stopped. I didn't hit the car. The car behind me was too close. They bumped into me, which then made me bump into the car in front of me. So you know. What? In what way?
You would get a ticket. You didn't leave enough space.
No, I did leave enough space. I didn't hit the person in front of me.
I didn't know.
Oh, you got it?
I would know.
Yeah, so the car behind me bumped into me, which then made me bump into the person in front of me. What was fun is the person behind me, their dad was a cop. Yeah. It was also like they'd already totaled a previous car. Anywho, they hadn't learned too many. Yeah, fun things, right? But anywho, great. Physics, right? It's important. Driving. Driving is the most dangerous thing you do. Don't forget that. It's so dangerous. Don't let it scare you, but respect it. Respect cars. All right, great. The rest of the problems in this section are just, do you know to go from angular to linear by multiplying by r? Can you do kinematics? You do a few of these, you're gonna be fine. So far, the people I've worked with, it seems to have gone very smoothly. It's just realizing there's 2 pi radians in a circle and realizing you go from angular to linear by multiplying by r. So on to new things. Yeah, for my class this morning, I realized, we got lots of time, which is a good thing. So, anywho, we'll probably finish earlier than I expected, but sometime next week. If you have a bolt and a nut that's stuck, should you use a long wrench, a short wrench, or it doesn't matter? If you've never had to do this, ask someone around you. Hopefully. I can't think of another example. This is fairly common. If not, it's a good life lesson. At some point, you should learn to change your tire, all the normal things. All right, 10 more seconds. All right, in 5, 4, 3, 2, 1. All right, so this is one of those. It is what it is, but I'll connect it to something you use a long wrench. Okay. So this is a good life lesson to learn. Long wrenches help if everything's really stuck. If you can make the wrench even longer, it makes it much easier. So what I'm going to connect this to is something that you are, maybe if you haven't done this, if I have a lever. A wrench is just a really long lever. As weird as that sounds. So I got this lever. I got this really, really long seesaw situation. So there's a guy named Archimedes, I think that was his name, and he made the statement, if I had a long enough lever, I could lift the earth. And so what happens here is this is something you all, I'm going to connect it to something you know about. Great, I want to make this left side lift up. What am I going to do to the right side? Push it down, pull it down. What's our fancy name for a push or a pull? Force. Awesome. You apply a force. Now, this force is going to act over this distance. This big old distance. If you have a force and a distance, what do you Like, what comes to mind?
Work. Work equals force times distance times cosine theta. Distance is in the same direction, so the angle here is 0. Yay, awesome. What's going to happen to this side? It's going to move a tiny little bit. The distance here is going to be smaller. Remember, energy is conserved. The energy I put in on the right side is going to come out on the left side. So the work on the left is going to these two works are going to equal each other. Work 1, work 2, they equal each other. Work 2 equals work 1. So if I have a smaller distance to get the same work, I'm going to get a bigger force. It's just conservation of energy. The energy I put into the right side comes out on the left side. Bigger distance, less force. Smaller distance, bigger force. This is how levers work. If you have a really big lever and you apply a small force, you can get a really big force. It's the same way, it's similar to that whole hydraulic cylinders and stuff like that. Those are much more convenient to work with. Why do I mention this? So what we're going to now connect this to is the bigger the lever arm, if you apply a force, you get something called torque. Torque is the fancy name for kind of how, if you apply a force at some distance, you get a torque. What does a torque cause something to do? Rotate. It causes something to spin faster or slower. Torque is the angular version of force. You apply a force, you get an acceleration. You apply a torque, you get an angular acceleration. So torque is what makes things spin faster or spin slower. The equation for it is going to be RF sine theta. And I'm going to explain why that equation is what it is. So we just explained bigger R, more torque. That's the reason bigger wrenches and all that stuff. So bigger R, more torque. Bigger force, more torque. The last example I gave you is to help you understand why a bigger arm gives you more torque. This angle is the angle between F and R. This angle is the angle between F and R. It's the angle between the other two variables. Theta between F and R. Literally the other two variables in the equation. I'm going to give you all a problem to help you understand why it's sine of theta. It's going to be really obvious once I give you 2 examples why that exists. And we can get the direction. We're going to practice that in a second as well. So there's a lot of things here. We're going to practice all of them. Don't worry. But yeah, this is the most important thing. Torque is responsible for angular acceleration. Force, regular acceleration. Torque, angular acceleration. If you apply force at some distance, it's going to make the thing spin. All right. So I'm going to try to explain this angle. I got to mention another thing here. The symbol for torque is tau. T-A-U. It's the Greek letter tau. It's in the Greek alphabet. Fun fact, the capital Greek letter tau is just a capital T. This is the lowercase version. Again, a lot of letters in the English language come from the Greek alphabet. Not all of them, but a lot of them. A looks like alpha, so on and so forth. Tau. It's a little tiny thing with a little top. It's like a T. Looks like a T. The units for it should not be surprising. It's newtons times meters. If you're like, how should that not be surprising? It comes from the equation. What's the unit for force? Newtons. What's the unit for R, for distance? Oh, look, it just comes from multiplying them together. Yay. Someone did raise the good point. It's the same units as work. Does that have any profound implications? I'm not sure. But anyway. All right, we're going to do the direction thing in a second. We're going to get to that, but I want to explain this whole angle thing first. We're going to explain both. So to do so, I'm going to steal this picture. I'm going to steal this force. Actually, I'm going to steal it from this one because it's all nicely together. Great. So I'm going to steal this picture. I'm going to move things around. All right. I haven't taught, I haven't mentioned this yet. R is from the center to where your force is. So to draw R, say I have some force going this way. Doesn't matter. There's my force. R is from the middle to that point. There's R. Wherever the force is acting, that's how you draw R. If the force was down here, then R would be this way. You know, middle to where you're at. That's where the force is. So that's how you draw R. And you can make it a little bit bigger to find the angle between them. All right, so here's a situation. My question is, what is the angle between R and F in this picture? And I'm not going to make it multiple choice because that just takes a little bit longer. But I want you all to try it out. So I'm not going to make it a top hat question. But think about it. Pro tip, draw this and draw R. You're going to have a hard time finding the angle between them if you don't draw the picture. And remember, angle is theta. So draw R, and then what's the angle between R and F? And then we'll do a different one after that. So for now, focus on the top one. Just worry about the top. All right, so there's the center. Remember, R points from the center to F. Great. There's my R. Center to F. I got two arrows pointed the same way. What's the angle between them? 0. All right, let's look at our torque equation. Torque equation is RF sine of theta. In this problem, my angle is 0. If you're not sure what sine is, so the question is, what sine is 0? If you're unsure, chuck it in your calculator. I don't need you to have this memorized. What's sine of 0 going to be?
0.
It's 0. So what's my torque? 0. If you all pull on a circle like this, is it going to spin? Like, this should not be hopefully a surprising thing. If you all have a circle, a sphere, a circle, a cylinder, I don't care what object it is, and you pull on the bottom of that object, it's not going to spin. Why is it not going to spin? Because my torque is 0. Why is my torque 0? Because the angle between these is 0. Like, you all know this. You all know pulling on a circle doesn't make it spin if you pull on the bottom of it. Why? Because the angle is 0. So that's why we care about this angle. If you're pulling away from the circle, away from the center, you don't make it spin. No torque. No angular acceleration. Not surprising, hopefully, if you've ever... A hula hoop, if you pull on it, it doesn't spin. Great. What about the one down here? So I took the same picture and I rotated F. So a new picture down here where instead of F being straight downwards at the bottom, I have F being directly to the left as much as I could. I think it's a little askew. Something like that. F is directly to the left. Go ahead and draw your R. Find the angle between them. If you don't draw the R, it's trickier to see. Draw a little dot. We make R. If you want, you can make R a little bigger. Makes it a little easier to find the angle. And it's this angle, which I purposely chose. What's the angle? 90. So if you all do the torque, it's RF sine of theta. In this case, my theta is going to be 90. Sine of 90 is 1. It's literally the largest value possible. If you all want to make something spin,
as much as possible, you apply a force perpendicular to the thing. And again, this is just like, if you want to make something spin, you all have done this. You apply the force on the side in this kind of direction. I'm sure you made things spin at some point in your life. So this sine of theta basically says, the more my force is perpendicular, the more torque I get. The faster I'm going to spin up my thing or slow it down. If I'm directly lined up with R, if I pull directly away, nothing happens. If I'm somewhere in between, I'm somewhere in between for torque. That's why this angle matters.
That's why we have this sine of theta. It's whether your torque is maximum or zero. Okay, great. Angle explained. Whether or not it makes sense, hopefully, maybe, I don't know. But hopefully it makes more sense than it did before. Next thing is the direction. The direction, I'm going to teach you all 2 ways to do this. The direction of torque, 2 ways to do this. One is like more official, one is it works. So I'm going to do the more official way first. I'm going to do right-hand rule. And the way I think about this, the way I like to do this right-hand rule, is point your fingers in the direction of R. So it works for any of the ones I did here. But let's just do this one. So I have a nicer slide, so we'll use this one. Point your fingers in the direction of R. So flat hand, fingers in the direction of R. Now, my fingers need to stay in the direction of R. So don't turn your wrist, because now my fingers don't point in the direction of R. I need to be able to think of R. I like to think of it almost like a door that I'm swinging towards F. So I need my door to swing towards F. Now, depending on your hand orientation, you can't do it. If your hand's the wrong way, and I can't bend my fingers backwards, that's bad. I can't do it. My fingers don't bend backwards naturally. If I have my palm facing into the board, I also can't swing my fingers that way. So you can basically rotate your wrist until, oh yay, I can swing my fingers. I can swing it like a door. Yay, which way is my torque? Out of the board. So point your fingers in the direction of R, and then you can kind of rotate your wrist until it works out. So fingers in the direction of R, so fingers this way, and then I want to be able to swing them. I almost think of it like swinging a door. They call this curl, like your hand's curling, towards that. So that's one way of doing it. One way of doing it is this, and that gives you the torque is, remember a dot is out of the board because it's like an arrow that's coming at you, like a bow and arrow. All right, the other way, and this one might be more intuitive, it's the exact same process at the end of the day. Is this thing going to have an angular acceleration clockwise or counterclockwise? If you apply a force and it's up to the left direction, which way is it going to want to accelerate, angular accelerate? Clockwise or counterclockwise? Counterclockwise. That's hopefully very intuitive. You apply this force, it's going to want to angular accelerate that way. Just turn your fingers that way and your thumb points in the direction. Same exact result. So if you prefer, it's going to angular accelerate counterclockwise, curl your fingers that way, your thumb points in the direction of torque. That works. All right. Try the other 2. Pro tip, make R a little longer so you can actually swing it. R technically just points to the outside, but to make your life easier, make it a little bit longer so that you can actually swing R towards F. Or again, decide which way it's going to spin, which way it's going to accelerate. And curl. So anyway, try it out. Fingers in direction of R. And then make it so your fingers can actually swing towards F. I can't, my fingers can't, it can't happen. Make your fingers so they can actually swing in the right direction. All right, I need my fingers to swing that way. I need my fingers to curl that way. 2 ways to explain that. That's the way it's going to angular accelerate, or that's the way R gets swung to F. So you point your fingers in the direction of R, and you make it so that your fingers can actually curl towards F. You can see look at that, now they point downwards. Yay.
If your hand's backwards, it can't, like, okay, I guess I kind of can. My fingers, I have pretty bendy fingers. Most people can't bend their fingers that far backwards. For whatever reason, I was very good at Mercy in elementary school. My fingers bend back really far. Yeah, it wigs people out, but they bend back really far. Most people, I don't know why. It was very useful again in elementary school. Since then, not very useful. But rule of thumb, most people's fingers don't bend backwards, so obviously that doesn't work. Curl your fingers so that they curl inwards. Long story short, my torque points into the board. Oh, and again, I'm gonna keep mentioning this. If the torque is in, the angular acceleration is in. In this one, the torque was out. And so my angular acceleration is out. What direction is angular velocity? Impossible to tell. You can't tell which way this is spinning. Just because you know which way it's accelerating, that doesn't tell you which way you're moving. If I told you I'm accelerating to the left, that doesn't tell you I'm moving to the left. I could be moving to the right and slowing down, or I could be moving to the left and speeding up. Acceleration is not the same thing as angular velocity. No way to tell. So I just want to continue to remind people of this. Acceleration is not velocity. Acceleration is not the direction you're going. Acceleration is the direction that your velocity is changing in. Very, very important thing. All right, try the last one if you haven't already. You need to draw the R if you use that technique of swinging R. So I'll give you like 10 seconds for that. So there's R, from the middle to there, and then just swing it. Yeah, you are going to get 3 different right-hand rules in Physics 2. One of them will use a similar technique. One of them will use a similar, like, curling your fingers. The others won't. Yay. Future problems. All right, so swing it that way, swing it clockwise. You swing your fingers clockwise, and your thumb's going to point into the board. In, my alpha is also in, my angular velocity, no way to tell. There's not enough information to tell what's going on here, which way my wheel's spinning. Now, if this wheel wasn't spinning and then I do this, it will start spinning that direction. So, anyway. All right. Now the real thing of I did a bunch of things and asked a bunch of questions. And did any of it actually make sense? This is for me more than for you. What is the direction of torque in the following image? I got a circle. On the bottom of the circle, my force is pointed mostly to the right. Is my torque up, down, out of the page, or into the page? All right, we'll go like 10 more seconds. Draw R and make it swing, or figure out which way this is going to rotate and curl your fingers that way. In both cases, your thumb gives you the direction. You get the same result either way. All right, we'll close it out in 5, 4, 3, 2, 1. All right, we'll close it out.
R points this way. Again, I exaggerated it and made it longer so that I could swing it that way. If you swing your fingers counterclockwise, your thumb points out of the page, and there you go. So, let's see how we did. Yeah, it's pretty good. All right, cool. Something I forgot to mention at the beginning of class, housekeeping-wise, I think, so this is complete aside, student perception of instructor SPIs are open. I very, very, very much appreciate if you all fill that out for me. It does two things for me. One, it gives me feedback, helps me improve as a teacher, just like the survey I sent you all. There is sadly no way for me to give you all extra credit for doing the survey because I don't get the reports till after. I don't have any way. It's all anonymous, which is good for you. Like, that's good. So be brutally honest in these SPIs. But yeah, they help me improve as a teacher. And then two, since I am now full-time here, they are something I can put in like my annual evaluations. So they do help me out personally. If you like me, fill it out. If you hate me, fill it out. I don't really care either way. I want your all's feedback. So really, really appreciate it. I'll send out an announcement or two reminding you all of it because it does help me a lot. It's really quick. Even if you don't do the answer stuff, it takes like 5 seconds. Anyway, I appreciate it. So if you're willing to do it for me, I appreciate it. Do they still have, so I was an undergrad here. Do they still have it where you can't enroll until you do them? Is that a thing? Oh, they got rid of that. Oh, maybe?
No, you can click do it later.
Oh, okay. There's a do it later. Okay. But that pops up every single time, right? Yeah. Okay, great. I remember that as an undergrad, and I was also annoyed by it. I remember that. It's like, I don't want to do this right now. I get it. But when you think of me and how much you love/hate me, and use that motivation to fill it out, because I appreciate it. Okay. This next slide, don't worry about it. It's just explaining the angle thing. Honestly, I already talked about that. Why do we care about torque? Chat about this, and then I'm going to give you all, we're going to do a quick problem, and then I'm going to tell you all about the quiz problem, just to make sure you're all prepared for it as well. There's a quiz problem on it. We'll literally do it if we have the time, then I'll do it next time. All right, why do we care about torque? It causes an angular acceleration. It makes things spin faster, spin slower. Just like why do we care about force? Forces result in acceleration. Torques result in angular acceleration. Yay! Guy discovered this. Guess who? It's our favorite, Isaac Newton. Woo! Look at him. What a guy. Again, he did so much. He not only did F equals ma, he also did torque equals I alpha. It's the same thing. So, no torque, no angular acceleration. Very, very important. All right, so here's an example problem on this. I got a beam attached to a wall. Then you'd be like, what? There's nothing spinning here. This wants to spin. Think of this thing attached to the wall. It wants to fall. And if one side of it fell, it'd be like a rotating rod. So this thing wants to spin about the wall. It's attached to the wall. I mean, I'm like, imagine your arm. If you held your arm out, what does it want to do? It wants to fall. And when it falls, that's like a rotating rod. As weird as that sounds. So there's a torque, even though it doesn't seem like it. So I got this beam. I got this little block at the end. And I want to find the torque. Now, great news. There is literally only one equation with torque that I've given you. It's probably the one we're going to use. Because it's the only one that exists that I've given you. So, great. We're going to use RF sine theta. Like, if it's the only equation with the variable we want, we're probably going to use it. What do I need to figure out torque? What variables do I need? Y'all tell me, they're the ones in the equation. We need force. What else do we need? We need the radius. And then what else do we need? The angle. Great. You know, it's the things in the equation. This is the benefit of, if you identify what you're solving for, and you have an idea of what equations have that, it helps you spot the givens. This is why we're like, our advanced skills, instead of just writing our givens, then what we're solving for, what are we solving for? And it helps us identify what givens we need. That's more so how the real world works. You don't just have a nice list of givens where it has exactly what you need. All right. What forces are there acting on my stuff? Gravity. That's why does it want to fall? Gravity. Now, Here's the thing. Gravity is acting everywhere on this. Oh my gosh, does that mean I'm going to have to do it 1,000,000 times? No. Because I taught you all that you can take an object and you can compress it to a single spot, which has a fancy name. Center mass. Now I have two objects here. See if you all can draw the center mass. Draw the arrows for the force of gravity. Draw it for the rod, where its center mass is. Draw the force of gravity there. And then draw it for the little box, because there's something very subtle in this problem that I can almost guarantee if I didn't do this problem, a lot of people would miss, because it's very subtle. So draw the force of gravity on this beam. You're going to draw an arrow, and where you draw that arrow matters. It should be at its center mass. Draw the force of gravity on this box. Where you draw that arrow matters. It should be at its center mass. Try that out first, and then I'll tell you the next step in a second. So you want to draw these arrows. Very important. If you don't draw them, it makes your life a little bit more difficult. All right. Now, I'm pretty sure everyone knows how to do this, but I'm just going to check. Where should I draw the arrow for the force of gravity for the brown rod plank thing? Should it be here? No. Where should it be? It's going to sound stupid, but the middle. Great. So let's call this force of gravity 1, because there's two objects. First one's 1. All right. What about this block over here? Is the force of gravity, is that good? No. Where should it be? Middle. This sounds like, why am I asking such silly, stupid questions? Like, so easy. They're the middle. Great. Why am I asking that? The next question, so to find torque, we need the forces. Now we need the R's. How far away are they from the axis of rotation? So they want to pivot from the wall. That's my axis. So draw an R from the wall to FG1. Draw an arrow from the wall to where the first force is. Draw an arrow from the wall to where the second force is. And then determine the values of them based on this picture. You have everything you need in this picture. I didn't even cover up the numbers. Like, the numbers you need are all here. What is the value of R1? What is the value of R2? And draw them on your picture to make sure you get it right. If you don't draw them, I can almost guarantee you'll make a mistake. All right, so R1 is going to point from the wall to F1. What's the value? If we're a dead center, what's the value of that R1? 1.5. 3 divided by 2. The thing's 3 long. Now the second one you got to be careful on. The second one is to here. It does not go the full length of the rod. So R2 does not equal 3. My arrow here is not all the way at the end of the rod. It's 3 minus, how far shifted over is that arrow? 0.1. And this is really subtle, and it may not seem like it makes that big of a difference, but if this mass was like 10 kilograms or something, it could change your answer a lot. So, pictures help. Pictures help. All right, now the rest of this problem is really straightforward. We got basically everything we need. So if you want the net torque, yeah.
So why do you divide that one by 2?
So this one I did divided by 2 because I'm halfway along the rod. So this whole thing is 3. So if I'm halfway along it, it's 3 divided by 2. Whereas this bigger arrow up here, this wooden rod is 3, and then this tiny distance here is 0.1, so I subtracted them.
Why is it like radius versus diameter?
Yeah, that's a good question. So here, R corresponds to how far you are from the axis of rotation. So R here isn't necessarily radius, it's just a distance. Yeah, that's a great question. So R here isn't so much radius as it is how far away, it's a distance from the axis of rotation. And the reason we use R instead of X or Y is if this thing's at like an angle, R is kind of the combo of all of them together. All right, so yeah, I really appreciate that. So if I want to find net torque, it's like net force. I have, how many torques are acting here? How many forces are there? 2. How many torques are there? Great. Now, the one thing you got to be careful of, and this problem, it doesn't matter that much, are these torques in the same direction or opposite directions? Just like our forces in the same direction or opposite directions. In this case, my first torque is into the page. So torque 1 is into the page. My torque 2 is also into the page. So I can just add them together. But if they were opposite directions, I would need to subtract them. Are the torques helping each other or fighting each other? You got to consider that. So we're going to say torque 1 is positive. We're going to say torque 2 is positive. You add them together. If they were opposite directions, you wouldn't add them together. All right. Now we math. Like now it's just torque net equals R1, chuck them in there. So step 4, torque net equals R1 F1. Oh, and the angle here is just 90 degrees. So I guess I'll write this all out. R1 F1 times sine of theta 1 plus R2 F2 sine of theta 2. The angles are both 90 degrees, 90 degrees. So now we just chuck stuff in there. We got all the numbers, easy peasy. So 1.5. Now it's the force of gravity, so that's going to be mg. So 2 times 9.8. I'm sadly not going to be able to fit this. Oh, it'll fit up here. Plus 2.9 times 1 times 9.8 times 1. And you plug all that in and you get an answer. 1.5 times 2 times 9.8 plus 2.9 times 1 times 9.8. 57.82 newtons per meter. I'm going to double check my work because I did it quickly. All right. I just want to mention to you all the quiz problem so you don't make a mistake and so you're not confused. So I'm going to show you all the quiz problem. I'm going to write it out really quickly. I'm going to tell you the mistake, and we'll see if I can tell you how to, yeah, it'll be quick. All right. My arm is at a 30-degree angle, and I'm holding a 5-kilogram mass. What is the torque on my shoulder? Ignore the... Assume my arm has no mass. It's just to make the problem easier. All right, arm's at a 30-degree angle, holding a 5-kilogram mass. What's the torque on my shoulder? First step to solving this problem is draw a picture just like we did before. Here's my massless shoulder and my massless arm. Here's my mass. Here's my 30 degrees. Why is it when I hold my arm out? Why does it want to fall? What's pulling it down? Great. If you're holding an object, it's really hard to hold. There's a force of gravity. The mistake that many people will likely make on this problem, which is why I'm telling you this, torque is RF sine theta. If you put theta as 30, it's wrong. Why is it wrong? Make R go out here. Theta is between R and F. This is the angle between R and F. This is R. There's my F. This is the angle you actually want. That angle is not, obviously that angle is not 30 degrees. You can tell that when you draw it. What is that angle? It's 120. How do we know it's 120? This angle right here is 30 degrees, add 90. Yeah, the key here is the angle is between R and F. If you just, remember, don't just chuck in the angle, and sine of 120 is not the same as sine of 30. They are very different from each other. All right. And yeah, we'll finish up, then we'll start the next step, and we are totally on track to be at a very comfortable pace to finish up things in a week. Hey, what's up? Let me